Morning, everyone. So yesterday we took another close look at mirrors. The different types here. We can have a plane mirror, which is the flat mirror. We introduced some of the language of your object. It could be you, it could be a candle. We introduced the notion that our brain sometimes plays tricks on us when we actually look at the shininess of a mirror, because we always interpret light as having traveling straight lines. Sometimes, depending on how these lines interact, it ends up creating a virtual image. It ends up creating a reflection of yourself inside the shininess of the mirror. I'm going to use this language of behind the mirror, but remember, we're not walking around to the other side. We're still looking at the shininess of the mirror, but we're looking at the sort of the reflected world inside the shiny mirror. For a plane mirror, we had introduced some of the language here. We called U the object. HO would be the height of the object. Your DO would be the distance for the object. When this eventually ends up making an image, we can have the height of the image. If the image happens to be upside down in this case here, it's where the light rays actually intersect. We actually have an upside down image, so it's inverted. Based on the size here, we're about 5 high, but this one's a 2.5 downwards. So this one here is a diminished. It's a smaller image here. So we're just going to have another look at these ray diagrams a little more for both concave and convex. And then today I'm going to introduce to you the equation that actually links some of these variables about the object, about the image. Remember, for a ray diagram here, you have to use a ruler, or else you're not going to get the correct intersection points. In this case here, currently my object is 12 away from my vertex. So far, the curvature here, I'm looking at a concave mirror. A concave mirror should be a converging mirror. It should be bringing light rays together, which I'm seeing. Remember, we don't have to draw all the light rays. We actually only need to draw 2 of them. So if you remember, for a concave mirror, a converging mirror that brings light rays together, if I have a parallel ray, it's going to strike the mirror. They're not even going to animate it here, but in this case here, technically I should be hitting the sort of the close side of the mirror here. And in that case there, it's going to bend through this point here called the focus. The focus is the point where everything bends through, right? If focus is there. We had other terminology here, like the focal length was the distance between the vertex and the focus, so that's about 4 there. The center of curvature, which we're labeling as CC, is going to be twice the distance to the focus. And we're going to use all of this in terms of the math later on. So far what I have here is my real light rays are stuck on the left-hand side of this mirror here. The real light rays here will hit the shininess in the mirror. I drew my 2 rays, parallel goes through the focus. I draw the line that hits the center of curvature. If I imagine this mirror here, it's just sort of continued. If I go through the center, I'm going to end up hitting the side of the mirror here head on. So 0 degrees on, undeviated, it comes back directly the way it came. Where it ends up intersecting is where my image is going to form. The image is what's created by the intersection of these lines here, depending whether the intersection is made of real light rays. We call that a real image. We're going to see later on some virtual images as well. It's basically because light rays don't actually travel through it. It's just our brain playing tricks on us. It just creates that image for us. So in this case here, it's a real image because I have a real light ray bouncing through there, a real light ray coming back the way it's unchanged. Again, there are many other light rays, but you just need those 2 rays. Where they intersect is where the image forms. This type of mirror here depends on how far I am. So in this case here, I was farther than the curvature. This is a real image. So if I put a piece of paper here, I should be able to see a nice clear image upside down of my candle. But what's going to happen here is, just like when you look at the curviness of the spoon here, I'm going to imagine slowly bringing myself closer. You see the light rays themselves are the same. I'm still doing parallel, I'm still focusing through, but as I get closer and closer to the center of curvature, the intersection point actually changes. You'll notice the size here has actually increased. When I'm actually on the center of curvature, that's going to be like the perfect, this will just look like a blurry point here, but I have if I put a screen, I have exactly the same height before and after. And as I now go between the center and the focus, you don't need to memorize this. You just need to draw parallel goes through focus, the line goes to center curvature, where they intersect is the image. Now what you're going to see is, again, it's a real image. Real light rays are bouncing on the left-hand side. But if you put a screen here, not only is it going to be upside down, now it's even going to be bigger than the candle before. This is going to increase pretty dramatically here. As I stand on the focus, this is the perfect point here where a parallel goes through focus. When I go through the center curvature, these 2 lines are parallel. These 2 lines will never meet. This one here will definitely have perfect like blurriness. You can't project it on a screen on the real side. We don't interpret it as coming from any image on the other side. It's a little more clear when I'm on the other side though. If I now am closer to the focus, if my eye is right up close to the curviness of the spoon, what's going to happen here is when I draw that line, parallel line through the focus or the line through the center curvature, while on this side it diverges, and this side I'm not going to expect it to come together. We're going to imagine these straight lines had come from an image, a mirror image inside the shininess of the mirror. We're going to imagine that the image is actually inside. You notice that they dot it for you here. They're trying to tell you these are not real light rays. The real light rays were on this side. They were bouncing every which way this side, but it's just our brain thinking. Because light travels in straight lines, it must, right, come from the image behind. So in that case there, these are dotted lines. This is now called a virtual image. You can't physically put a screen inside the mirror surface. You can't stick it physically into the shininess. So you can't project it on a screen because it's not a real lines, but our brain interprets it as if it has come from behind. This image here you can describe. The image distance is actually farther than the object distance. It's 4 away. I'm only 2 away on this side here. The magnification here, I'm actually getting bigger. And I'm also upright because I'm also standing tall. And as I get closer and closer, the image sort of responds that way. I'm going to post a simulation on the website later on so you can play around with especially different distances, different objects, and whatnot. For this website here, they also do Convex Mirror. They're a little clever. What they're going to do is instead of standing on this side, let's imagine we actually stand on the other side. So in this case here, now we flipped everything around. Now let's pretend our real light rays here on the right-hand side. We're looking at the same bulge, but we're looking at sort of the bendy side towards you. And what we're going to do here is we're going to draw a ray diagram for being on this side. So a convex mirror, this time the right-hand side are the real light rays. Our real light rays end up diverging because a convex mirror is a diverging mirror. We saw that this one here, it didn't matter what your DO was. What's going to happen here is your image, when I draw that parallel ray, it ends up reflecting off as if it had come through F. When I draw the ray through C, it's going to be undeviated. It's just going to bounce back the way it came. On this side, it's always going to diverge. So on this side, it's our brain that actually interprets, well, even though there's no real light rays that actually come together, we can't project it on screen, these straight light rays here seemingly have come from behind the scenes, and what we have is a virtual image. So although I can't put a screen here to actually show a picture of that, it's more simple. When I actually look at the shininess of the mirror, I actually end up seeing an image that's tinier. And this doesn't matter, no matter how tall or short the object distance is, doesn't matter how far away I am, I'm always going to get an upright image, and I'm always going to get it smaller than what it was before. So just draw the two ray diagrams here. Sure, the lines were a little bit different between concave and convex, but if you can draw those two, figure out where they intersect. If they're on the same side, it's real. If they're on the opposite side, it's going to be virtual. And then you can talk about, is it shorter? Is it upside down? Things like that. We actually see store mirrors are usually concave, like convex like this. Same thing you see in parking lots here. Basically what ends up happening here is for a store mirror, instead of just having a plain mirror, which is nicely oriented and nice mirror image of the entire store or the parking lot or whatever, what's going to happen here is if I have a slight bulge to it and I'm looking at the bulgy side, something that has a real height will actually look smaller in the mirror, so therefore I can actually see more of my store than say I would with a plain mirror. Or for a parkade, you put a mirror not just to see around the corner, but if it's a bulge, it ends up being able to capture more of what's around the parkade inside of smaller images when you look at the shininess of the mirror. All right, so we're going to start dealing with some of these image characteristics here. None of this you need to memorize. We're going to see an equation that links some of these variables, and we also can just draw a ray diagram. One emphasis, however, is this will always be done on grid paper. You have to use a ruler. You have to make sure, let's say, the focus is halfway to the center curvature to make sure the intersection is in the right position. So with that intro here, let's just have a look at our mirror lens equation. This same equation, it's on your formula sheet. It'll work for both, as the name suggests, mirrors and lenses, but we're just going to practice it this time. We'll introduce it here. Turns out for the mirror lens equation, we're going to have the expression 1 over f, 1 over the focal length, is going to equal to 1 over di plus 1 over dou. So that's our mirror lens equation. F here is going to be the focal point, or the focus if you like, focal length if you like. The di, as we saw before, this one here is called the image distance. And then the DO is therefore the object distance. So just like with any of our formulas we've seen, if you have 2 out of the 3 of them, you can solve for the other one. It's a little bit more confusing because of this reciprocal relationship, but it's not overly bad. A couple other notes as we step through some questions. Careful, the focal point is always going to be 1/2 the distance to the center of curvature. So you can sometimes call it the focal length as well if you like. The distance between the vertex and the focus is called the focal length. It's going to be halfway to what would have been the center. That's marked by the curvature of the mirror. It's possible your mirror is actually more elliptical and sort of curvy shaped here, but there would be some corresponding curvature. For the focal length, this is super important. We're going to use a convention here for positive focal length. Positive always refers to the converging type. And if you remember for a mirror, the converging type here was actually a concave mirror. So if any time your focal length comes out positive, you know right away this is the type of mirror we're looking at, concave. It's the type that converges. If the focal length comes out negative, it just means the focus is on the other side. This would be equivalent for the diverging of that device. And in this case here for the mirror, we're looking at the convex. We're looking at the bulgy side of the mirror. Although we're going to use the exact same formula for lenses here, converging still is positive, diverging is negative. For a lens, we're actually going to see it's actually a convex lens that actually converges, or a concave lens that actually diverges. So just be careful, mirrors and lenses are also opposite. So we define these ones here. Image distance, object distance. Technically, you could use meters for both, but seeing as we're just setting up a ratio, typically the image distance is just quoted in centimeters. That way we don't need to be meters away from the shininess of the mirror, but it's just a ratio anyway. In this case here, by convention, we're going to use a convention that real is positive. This is just sort of giving you some background with how to use this formula. Anything that is real, like light rays going through it, intersecting on your side of the mirror, your object is always going to be real. Your candle is always physically real. It's always going to be on the side that's emanating the light rays. So this one here is going to be always positive. So if you end up with a DO that's negative, something's wrong. For the image distance, however, this is sort of where the projection ends up. The projection could be on your side. If it's on your side, if it's positive, it's a real image. That means actual light rays pass, and therefore you can project on screen. If you put up a piece of paper at that particular position, you can actually see a nice scan of that picture. If it's negative, more often the case here, if the image distance here if this one here ends up as a negative, it means it's a virtual image. It means this is just our brain playing tricks on us. There actually aren't real light rays and you can't project it. So in this case, a virtual image here, there's no light rays, or not enough light rays intersect. No light rays intersect, and you cannot project on screen. That would be similar to looking, it looks like I'm inside the mirror itself. Because it's inside the shininess of the mirror, you can't physically reach into the mirror and actually put a screen up there. So it's just our brain playing tricks on us. We'll go from there. So just want to get you some familiarity with this formula here. We'll see a formula for magnification come up in this question as well. So let's start off here. A candle is placed 15 centimeters from a concave mirror. We're only going to deal with mirrors for now. We'll deal with lenses in a later lesson. So from a concave mirror, with focal length. So the distance between the vertex and the F point of 7 centimeters. So this is like the first ray diagram I drew. I'm actually more than twice the distance of the focal length. They just want you to calculate here, find the image distance. Find out where that appears. Let's just go through the math, and then we'll draw the ray diagram to verify. So far, our math here says 1 over F equals 1 over di plus 1 over do. Double check for yourself here. This is a concave mirror. We're looking at the cavey side of the mirror, the entrance of a mirror. This one here is a converging mirror. Because we know it's a converging mirror, it should have a positive F. So in this case, when they give me a focal length here of 7, I can leave that as a 1 over positive 7. If this one here, the same style question, but if I put a convex mirror, you would have said diverging means negative. You would have put it negative. So make sure you're just clear with your positive and negatives here. We have 1 over di. I don't know what my image distance is, so let's just go 1 over di here. Plus 1 over do. Object distance is always on the correct side of the mirror. It's always the side that's emanating the real light rays. So this one here will always be positive. So obviously you can do common denominators, whatever. I would just do this as fractions. So 1 over 7, as decimals. 1 over 7 is 0.143. That's equal to 1 over di plus 1 over 15 is equal to 0.067, give or take. If you can keep the numbers in your calculator, even better. So 1 over 7 minus 1 over 15, that gives you 0.076, give or take. That's not the di yet. That's still the reciprocal of di. I use centimeters for all of this because we're just setting up a ratio. So the DI will come out in centimeters. I take the 1 over of this decimal that we get, and we can avoid the common denominators here. My DI happens to be, give or take, about 13 centimeters. And my DI is positive, so that tells me that the DI is on the real side. Let's sketch a ray diagram to make sure we're on the ball here. So in this case here, our principal axis, we would have our, we're looking at the curvy side of the ruler. I have my candle. I don't necessarily know how tall this is just yet in this question. I know my object distance is a positive 15, right? I'm on the left-hand side of the mirror here. I'm on the real side of the mirror, right? The shininess here is on the, I'm staring at it. So that's where we have here. The focal length was given to you at 7. So wherever 7 shows up here, that's where F is. Remember, the focal length is halfway to the center of curvature. If I double that, so at 14, that's my center of curvature. Using a ruler, do a parallel line, go through F, do a line that goes through C. See, if I don't use rulers, it's really bad. So if I go through C here, this one here should be undeviated. This one here should come directly back the way it came. Obviously, in this case here, the mirror would have to actually extend. The mirror would actually have to be a little bit lower like that. But where they intersect is where I'd expect my image to be. My image is going to be upside down. We'll see that in a second here. It's upside down, but it's actually closer than me. It is still on the positive side. For mirrors, the positive side, the real side is where your real light rays are. The virtual side is sort of behind the mirror. It's in that sort of reflected in the shininess of the mirror. So my distance of object is positive 15. I notice my image distance is positive 13. That means my image is still on the positive side. Because it is a positive and it's a real image, you can take your screen and you can actually get a nice reflection of the candle, and you can actually project that onto the piece of paper. So there we go for just doing from the focal length, from knowing how things bend through this F point, I can actually, knowing 2 of these variables, I can find, in this case here, the image distance. Why is it important to know the image distance? We link it with a second equation, also on your formula sheet. We can actually get something called the magnification. This is the, is it bigger, is it smaller? And in this case here, also on your formula sheet, we're going to have M. The magnification is high over whole equals negative di over dou. Again, this expression will work both for mirrors and lenses. We're just applying it to mirrors at this point. Basically, what magnification says here is it takes your image height, it takes how tall this image is. So in this case here, we see that the image is actually shorter, it's actually diminished, smaller than the original. Takes the image, and it takes a ratio of the object height. That's going to give you some fraction. Right? In this case here, we would expect a magnification of something less than 1, because we're actually going to be smaller than before. But the relationship between magnification, not only how different the heights themselves are, it's also related to the object and image distance as well. Careful, there is a negative that changes the sign as well, like we just did here. This DI here is going to be the image distance. And the bottom one here is going to be the object distance. So we can actually get a feel of the magnification. Are we larger? Are we smaller? Let me just introduce you the language here. If the magnification, this is always going to be a positive number, right? It can't actually, the high over whole would be positive. So magnification, if the magnification is bigger than 1, we say the image has been magnified. We say the image is now bigger. If the magnification is between 0 and 1, this one here means diminished. It means the image, when you actually manage to reflect it on screen and project it, it actually is smaller than what you had before. Although the magnification has to be positive, we saw that HI sometimes is negative, HO is sometimes negative, depending on DI and DNO. It's just by the time they do the ratio, they have to end up positive, especially if HI is negative. So let me just make this note here. Image height, if negative, it just means upside down, or the language we're going to use is it's inverted. And if we saw negative for DI, it meant virtual. So I should put that down as well. Image distance, again, if negative, those are the ones that can be negative. It is a virtual image. It means the image is actually just my brain playing tricks on me. I think it's actually hitting inside the mirror when it actually, no real light rays are actually going through there. So let's just practice through another question here and playing around with the second formula with magnification. These two formulas work together sort of hand in hand, so you might need to sort of, like a puzzle, solve through the problem. Let's take a 3.5 centimeter tall candle is placed 12 centimeters from a concave mirror. Oh, sorry, convex mirror. There's just those two curvatures, so convex mirror. I'll give you the center of curvature with that CC point, center of curvature at 8 centimeters. They want you to, in this case here, find the image distance, just like we did earlier. And this time I want to find wherever the image shows up, if it shows up, how tall is the image, is it upside down, is it right side up, things like that. I always try to take a paragraph here, see if you can label the variables. Super important in this section, or else you start getting positives and negatives wrong. In this case here, we're told our real object, which is a candle, is 3.5 centimeters tall. This one here is going to be the HO, positive. It is placed 12 centimeters, so I'm putting the real candle in front of a mirror. So this one here is going to be DO. I am expecting this to be positive, because it's up to me how far I put it away from the mirror. This is separate from a convex mirror. A convex mirror means I am looking at the bulge, and when I look at the bulge, this is going to be a diverging mirror. Light rays end up hitting this one here, will end up separating. Because a convex mirror is a diverging mirror, you can make a note to yourself here. Because it is diverging, color code it. Because it's diverging, I would expect the focal point is negative. And what that implies here is if my object is 12 centimeters, and if this side's the positive side of the mirror, that coincides nicely because the focal point, the center of the circle would have been inside, it would have been negative, and the focal point is also inside. I would expect the F to be negative. So if they had given me a focal point here, this time they give me center of curvature, even though they just gave it to me as a positive number, C should actually be a negative 8.0 because C is actually going to be inside the mirror. That's your C. The F is also on the negative side of the mirror. The negative side of the mirror is always the other side of the mirror. So the focal length, even though they're not giving it to me, I had to put in that negative myself. Mathematically, you can still solve it with a positive 4, but you're just going to get the wrong answer. So we use the center curvature, I use the negative, and now all we're looking for is the missing variables, image distance and image height. So let's just plug and play here. 1 over F is equal to 1 over di plus 1 over do. And we also have magnification, high over ho equals negative di over do. That's the relationship. Also for lenses, basically going to repeat of these two lessons. We're going to draw ray diagrams for lenses. One's going to be converging, diverging, and we'll worry about positive and negatives then. Let's see what information we have. So we go 1 over a negative 4.0 is supposed to be 1 over the image distance. This time I again have the object. The object is 12 centimeters away, so I know it's 12. So almost identical to the one from earlier, except for the fact that this time focal length is negative. We can solve for di. And once I have di, I may not necessarily know what hi, ho are, but if I have this ratio, I can figure out magnification, and magnification can actually give me my link to hi. So let's have a look here. Again, just do this as decimal. So I'm going to go 1 over negative 4. I'm going to minus off 1 over 12. So 1 over di, horrible looking number, 0.33. If I take the reciprocal of that, 1 over that gives me a di of negative 3. Again, because I use centimeters inside, this distance image is coming out as negative. So this negative came out of the math. This negative now means it's a virtual image, and that's what I would expect to see from a ray diagram. If I have a light ray bouncing off, I would imagine this had come from the focus, a line that's aiming towards the center of curvature comes back undeviated. It would have been an image that's actually inside the mirror. Because these are dotted lines, these are not real light rays, this is just our brain playing tricks on us. This is a virtual image. You can't physically put a screen inside to project it. Now that I have the die, I can solve the rest of the problem here. Let's find the magnification. The magnification is going to be negative of di. So negative of that negative divided by your object distance, which is 12. Your magnification, by the time you get that ratio, should be positive. So 0.25. 1 would be like an equal height. In this case here, because it's less than 1, I'm actually smaller. The wording we're going to use is diminish. Diminish means tinier. You will need to be able to state these image characteristics. So by the time our object, this time it was a candle, our image is tinier, our image is shorter. That's what our ray diagram predicts. We can also predict, because I was given a HO, I was given a HO, a height of the object, I can actually figure out what the HI is. So given a magnification of 0.25, this is equal to height of the image, I don't know. I'm expecting it to be tinier. The height of the image, what if I was a quarter the size and my object itself was 3.5 centimeters? So therefore the high is 0.25 times 3.5 gives you 0.88 centimeters. Right? So based on the magnification, I don't just have to say, oh, it's tinier. I can actually figure out how tall would my picture look like if I could take a ruler, if I look at the shiny side of the mirror, how tall is that image? So on your worksheet, you're going to get a lot of practice with this here. I'm going to end off with one last question. Same sort of formulas, but the math is just a little bit harder. But let's just see if we can work our way through. A 5 centimeter tall object produces a 12 centimeter tall image. So my candle realistically is only 5 centimeters. It's just after it bounces in the mirror, it ends up generating something that's magnified, something that's larger, more than double. The focal length is positive 15. I'm going to emphasize that positive. They would just say 15. So positive 15. This time the unknown here is calculate the object distance. Remember, with all these formulas, you can have, as long as you know all the other letters, you can find the one missing one. Calculate the object distance and identify the type of mirror. Right? If you are really familiar with ray diagrams, you can probably predict it already. So there's two ways I can end up getting an image that's taller than me. So in this case here, this is just us thinking. So when I had a concave mirror, if I were too far away, I ended up getting images that were tinier. If I were somewhere closer, I end up with things that are taller, so that's possible. Or I could be a convex, and if I'm convex, again, you would just do this with ray diagrams. You don't need to memorize it here. Your image ends up inside, but it's actually shorter. So based on these sort of guesses here, I would have imagined that I'm actually concave. Another thing that verifies it for yourself here is focal length is a positive number. Because the focal length is positive, positive actually implies it's the converging type. And for a mirror, the mirror that actually converges, brings light rays together, is actually a concave mirror. So that first question here, either you're familiar with ray diagrams or you just look on the positive or negative of the focal length, you can deal with that part, no problem. Regardless though, if it's a concave or convex, your formulas still work. We're going to still try to do 1 over f equals 1 over di plus 1 over dou. And we have magnification is high over ho equals negative di over dou. All right. Let's see where some of these other values are. This is the height, so the tall of the object, so this is HO. And my height of the image is actually 12 centimeters. You'll notice this time they just said the image is 12 centimeters. I don't necessarily know, is it positive? Is it upright? Is it actually standing straight up? Or is it actually upside down, negative? I don't know. The image could be 12 centimeters on the same side or on the opposite side as well. So let's just punch through our values and see what we have. On the left-hand side, I have 1 over, we're going to keep that as a positive because they said focal length is going to be positive. The 1 over distance of the image, I don't have that. And I don't have the object distance as well. So far I can't use that formula. Let's try the other formula then. So your magnification is given by the height of the image. The height of the image happens to be 12. Right. The object image is going to be 5. This is supposed to equal to negative di over do. Right. Technically speaking, I just gave you the height of the image. We can just treat this, just for simplicity's sake here for this problem, because it is a positive. Let's ignore the problem of maybe it's upside down and bigger. If you try doing that, you're actually not going to get any reasonable intersection. So we're just going to treat it as an upright thing. So let's say it actually stands the same orientation as I am, so 12 over 5. If I ask you for the magnification number, you can just do the ratio on the left side. 12 divided by 5 here is actually going to be 2.4. That's supposed to be negative di over dou. I don't have di or dou. But like we've done earlier in the course, if I have two expressions with two unknowns, I can rearrange this to isolate for a certain variable. In this case here, I'm interested in calculating the object distance. So maybe what I want to do here is I want to just isolate here. What would di be in terms of do? bring the DO up, so 2.4 DO, bring the negative over, that's equal to DI. My first expression, although I can't say for certain, here's your number or here's your number, I can actually say wherever I see DI, I can actually sub in the relationship, given the magnification, given that I'm assuming upright. So you can say assume upright. You can try this again here with the negative and see what you get. Assuming upright, I can punch in a negative 2.4 DO for wherever I see DI. I see a DI right here, so I'm just going to punch it through here. Still a little bit of math. 1 over 15 has to be 1 over negative 2.4 DO plus 1 over DO. That looks really scary, but again, we can just convert to decimals whenever I need. I'm just going to type in this part first, the 1 over divide negative 2.4. That number is going to be on top, so that's going to be negative 0.4167 repeated, all over DO plus 1 over DO, actually equals to 1 over 15. I can type that in, 0.067. And even though the math itself is going to still look a little bit scary here, what we're having is just common denominator. So that's both over D naught, so I just go 1 minus that number. So 1 minus a, double check my numbers here. I'm getting on top 0.583 all over D naught is equal to 0.067, and therefore finally the object distance, which I expect to be positive, right? Objects are always real. 1 over 15, oh sorry, take this answer divided by 1 over 15. So I'm getting an object distance of 8.75 centimeters, and I am positive. Right, so positive means real, right? Object is supposed to be real anyways. So let's just sketch out this ray diagram. Let's make sure we're consistent here. So you don't always have to do a ray diagram, but it helps you just sort of predict whether we're on the right track or not. I'm looking at a concave mirror, so I'm looking at this mirror. This concave mirror here, we found the focal length was 15, so the F point here, this is 15 away, so that's where F is. If you want to see center of curvature, that would then be 30. I am standing at an object distance of 8.75. As expected, I'm right up close to the mirror, so this is where I am. And if I draw my ray diagram, a parallel ray tries to reflect through F. A light ray that goes through C will be undeviated. They won't intersect on this side, but our brain's going to think about it came from behind. We would end up with an image that's taller than me. It's a virtual image because it's behind the screen. It's magnified, so it's 2.4 times bigger. That's why I got the 12 as a height. And the image distance we had said, actually I didn't calculate it yet. You can actually go, what's negative 2.4 times this 8.75? The image distance DI, you just punch into that formula there. The DI actually corresponds later on to a negative 21 centimeters. So this one here is going to be behind the screen, but 21 centimeters. Because your real light rays here are stuck on this side, we just have virtual light rays, we just have sort of dotted lines. It's just our brain thinking light travels in straight lines. It can from that singular point there. Right? So your worksheet will have a lot of practice with this here. We're going to spend our next few lessons, we're going to introduce ray diagrams for lenses in the next lesson and also play around with some of this math, but exactly the same formulas, exactly the same assigning positive and negative. So if you have any questions, just let me know. Thanks guys. Take care.